So the final module that we are going to talk about are what are called hybrid methods. Okay. So of course we need to motivate what hybrid methods are and give a particular example of a hybrid method. So what does the word hybrid imply? So far we have studied individual methods. We started with integral equations, and we looked at finite element, and we looked at finite difference time domain, right? Each method has their plus and minus points. Hybrid methods are methods where we combine combine at least two methods so that we can take advantages of both methods into one sort of a formulation. Okay. In particular, this module we are going to see how to integrate finite element method with boundary integral method. Okay. So let's try to motivate the more specific reasoning behind this. Okay. So what are these methods and why do we need them? So we can take any example. A particular example that I will take is that of a scattering problem. Okay. So scattering problem, a typical problem is, for example, there is a aircraft, right? This is supposed to be an aircraft, and it has some various components inside it. And what are we trying to do? We are trying to find out the RCS of this object. Okay. Now, if I were to solve this, so let's take a realistic case where I should not consider the entire object to be made out of one material, right? Like an aircraft, it will have a metallic frame, it will have a glass cockpit, it will have some plastic components, a rubber tire, all of it, different components. So realistically, I cannot just discretize the boundary of this object and solve the problem. I need some volume method. So what are the volume methods that we know of? Something that can handle epsilon r as a function of space. What are the methods that we know of? There is volume integral method, and then there is finite element method, where I go inside and discretize the interior of an object, right? And these boundary integral methods, supposing I want to use a surface integral method for this problem, what will be the problem? In integral equations, right, I can say that I will make my unknowns using Huygens principle to be the outermost boundary of this. What is the technical difficulty in this if I use surface integral formulation? Boundary may be complicated. What is the more difficult challenge? Green's function for that medium will not be easy to calculate. I know Green's function for free space, that's easy to calculate, but Green's function for a heterogeneous medium is not possible. So that's the technical challenge. That's why I cannot do surface integral formulation. So my two options are FEM and volume integral formulation. Okay. So let's take, and what are the main differences between FEM and volume integral in terms of computation? Right, FEM gave me a sparse system of equations, volume integral gave me a dense system of equations. So in terms of speed, FEM was very fast, and volume integral is much more time consuming. So at least for engineering problems, very commonly you would use FEM, and many commercial software use FEM. Okay. So if I wanted to solve this problem, right, so this is, I am asking what is RCS of this problem. This is the problem over here. This is the problem that I want to calculate. Okay. Now if I wanted to solve this problem using FEM, how would I do it? You don't have to list all the steps, but what is the main step? So let's say that this is, let's just make our aircraft once again. Okay. Break it into triangles. Okay. So break, but first of all, before I break something into triangle, what is the domain of interest now? Is it the boundary of the aircraft or a little bit more? A little bit more. Why? Because I need to apply the boundary condition, and the simplest boundary condition which we have learnt are absorbing boundary conditions, and for that we have seen that there needs to be a little bit of air gap between the object and where I terminate the boundary, right. So I may have like a boundary like this. Just for simplicity I am showing it like a circle, but it can conform to the shape of the thing, right. So this is air, this is the object, and now this whole domain has to be fractured into triangles, okay, and so on. in the case of finite element. And this is how I solve it. This is the sort of outermost boundary on which apply RBC, okay, and this gives me a sparse system, okay. And remember the problem with volume integral was, so in volume integral what would be the boundary that I have to choose? Just the aircraft, right? So, it is just the object, but the problem is dense system of equations, right. So, this is a plus point and this is a negative point, dense system of equations, right. So, you will find that this becomes impractically difficult to solve, because to solve a dense system of equations, what was the complexity, if you remember? Roughly it is little bit less, but it is order of n cube, and for the sparse system of equations it is n or n log n? It is more like n log n, okay. But still, I mean, log n is a small number. So, as n becomes larger and larger, you are going to a 3D aircraft, a 3D ship or whatever, n cube just becomes too much. And the storage requirement is also a dense matrix. I have to store n squared elements. Here I have to store like a scalar times n, because only sparse entries are there, right. So, that is why you are going ahead with FEM, and but this was the plus side, and the minus side is I have to discretize air. So, that seems like a bit of a disadvantage, okay. So, when we come to integral equation methods, okay, so by integral equation methods I am particularly talking about surface integral methods, okay. So, surface integral methods. In surface integral methods, so let us say this is my object over here with this boundary is defined to be some gamma. So, what was my approach in this case? So, let us say this is volume 1 and volume 2, sorry, inside let us call it volume 2, and inside, I mean outside it is volume 1, inside it is volume 2. So, we had come up with a couple of equations. What was the name of those equations? Extinction theorem, right. So, we use the extinction theorem. Extinction theorem was used to solve for the unknowns, right. What were the unknowns? Tangential fields where? On the boundary, right. So, unknowns were tangential fields. So, in a 2D problem, let us take 2D, so and let us make it Tm. So, what were my unknowns? There was a h tan, which is a vector, and a Ez. These are the two unknowns. Remember, if you recall the surface integral equations, my variables back then were grad phi dot n hat and phi. These were my two unknowns, right. Phi was my Ez and this was proportional to h tan. We had worked it out. These were my two equations. In addition to this, what else I needed was the Green's functions g1 and some g2. g1 was free space, so therefore easy, and g2 however for a heterogeneous object not easy, right. So, hetero object, no, there your differential equation, if you remember, del squared, let us say g plus k squared epsilon r g r prime is equal to minus delta of r prime. This guy being a function of space, even if you discretize it, you cannot get you can definitely not get an analytical expression for this g. At best you can get numerical values for this. So, if you want to use this approach, you will have to numerically calculate this g2 every time. So, in order to solve your problem, you have to first solve at every point you have to go and discretize your epsilon r. Discretizing the boundary, correct?
And then using G1 itself.
No, G1 and G2. The
Yeah, G2 means you change the K to whichever the value is.
Right, okay, so I should clarify this. In the surface integral formulation which we have studied in the previous modules, the object, the second object, that was volume 2, was a homogeneous object. Okay, so for free space, what was my Green's function? G1 was of the form Hankel function of K r minus r prime, right? Some constants were there, and let's call it, so when the medium changed but it remained homogeneous, then I could replace this K by the K of that medium. But if the medium is heterogeneous, not homogeneous, then K has no meaning. It's actually this whole K squared epsilon r, right? So then it's not going to be this Hankel function. In fact, you cannot write it in closed form.
Then how will we ever approach the surface integral?
So surface integral, that's what, surface integral equations are very useful when the objects are homogeneous, which can happen in some cases. If they don't happen, then you will go to some volume discretization method like FEM or volume integral, because calculating this G2, it can be done, but it can be done numerically only, which is expensive. So you don't choose that, right? So G2 can't be used. Okay. So now question is, if you look back, FEM had a very good advantage that it gave me a sparse system, can quickly solve it. Okay. But this extra air region had to be discretized. Apart from discretizing air, was there any other problem with it? With the boundary, yeah, what about the boundary? Yeah, what is the problem with the radiation boundary condition? Correct, right? So our boundary condition which we derived was exactly true when the wave hits it head on. But if a wave hits it at some angle, we have seen that the error is non-zero, right? So apart from discretizing air, I have the problem of inexact boundary condition. Whereas when we looked at surface integral formulation, we didn't have any problem of boundary, because the extinction theorem was the exact relation obeyed by tangential fields. We did not make any approximations, we did not have to include any air, it is exactly the relation, right? So when I say can we do better, what would be your suggestion? I want to make use of the advantages of FEM and the advantages of surface integral formulation. So if you are thinking like an engineer who knows CEM, what would you do if you wanted to remove the disadvantage of both of them? The edges of the triangle do form the boundary, yes. Now so you are saying that we start with this domain, this entire domain?
No.
Oh,
You just need the
just okay. So your suggestion is start with the boundary like this, then
and then discretize into triangle.
discretize into triangles, all right, then
Then I still don't know how to get G2, but I think it goes around the band.
okay. So I think we have some sort of building blocks are correct. So we want to use FEM for interior of object.
So do we have to like travel along all the edges of the triangle?
Yeah, in the case of FEM, the boundary condition applies to every element on the boundary, obviously.
No, yeah, in the boundary.
Yeah.
But I'm talking, you have to go inside as well.
Of course, you have to go inside. Yeah, you have to discretize because how do you FEM system of equations? The entire computational domain is broken up into triangles.
So in surface integral, right?
Yeah.
So you can subtract each integral of a triangle.
So your suggestion is to use the suggestion is to use boundary integral only, but to make it into piecewise homogeneous regions and do a multiply connected region and unknown tangential fields on everything, right? Yeah, that can be done. That's going to be very, very tedious. Okay. So what we'll do is, you were on the right track and then you deviated. Use FEM for the interior objects. That means I discretize the interior boundary. Okay. Left is what? I have decided I don't want to pay the price of discretizing air and I don't want to pay the price of inexact boundary condition. So the part of the FEM where I impose the boundary condition is the part which, instead of applying a ABC, I somehow use the boundary integral equations because they are exact and they are along the boundary. So this is the trick of, this is the conceptual idea. Okay, so use FEM for the interior objects and use, so I'm going to start, instead of calling it surface integral, the literature calls it BI, boundary integral. Okay, use boundary integral for boundary conditions instead of ABC. That's going to be our approach at the high level. Okay, so now we will go a little bit more into how can we actually accomplish this. But the motivation is clear. If we are somehow able to do this, then we would have not discretized air and we would be taking advantage of exactness of boundary condition. Okay.